Welcome. Now that we have already discussed the basics of the electric charge, the Coulomb law, and the superposition principle, we can now begin discussing what we call the electric fields. Now, electric fields can be a little bit tough to understand at first because they are quite abstract. They are not something that we are all that used to, but as it turns out, they are extremely powerful. So let us, before we go into the mathematics, let's just talk qualitatively about electric fields. Whenever we have some charge, I'm just drawing a point charge right here, right? Some charge Q or big Q, it doesn't matter. You can choose whatever notation you want. Whenever we have a charge anywhere around it, if we place a different charge, it's going to experience a force due to this charge right there, right? We already know that. That's Coulomb's law. So whether we put a charge here or here or here or here or there or there or there, it doesn't matter where we put it. Anywhere we put it, it's going to experience some force. The force, of course, will depend on how close they are, how much charge those objects have. But the point is that they experience a force. And that is quite interesting because one might ask, well, how does this particle here know that there is a different particle elsewhere? If they are separated in space, how does this particle even know about the existence of that other particle? And now that question is actually a lot deeper and a lot more difficult to answer, at least in a more philosophical way, than one might be comfortable with. But at least for now, right, a proper explanation does require some very advanced physics. But for now, what we can imagine is going on is that the entirety of space around not only this charge, but every single charge is permeated, right, is filled with something that we call an electric field, right? And how do we draw it? Well, if we were to put a charge here, then it would be, whoops, I didn't mean to do that. Then it would be pushed in that direction if it is positive, right? If both charges are positive, then it would go in that direction. So what we can do is we can draw a line going from our source charge, which is this one, right? This is the source charge. That is the charge that is at the source. And then we have a charge that we use to test what is going on. That is the test charge, right? Those are names that you may hear often. Okay, and then we just move this around. Well, what happens if I put it over here? Well, then it will go in this direction, right? Some books and some teachers like to use different lengths for the arrows, depending on how strong or weak the field is, right? The further away it is, the weaker it is, so they may use shorter arrows. I'm not using that notation, I just want you to understand the general idea. Right, and again, if the charge were here, it would go in this direction. So what you end up having is that you have something like this. And that is one way to represent the electric field. Of course, in principle, the further away you go, the weaker it is, right? Some people represent it like this, just with arrows that become smaller and smaller. But of course, since this happens everywhere in space, you can't really draw an arrow everywhere, right? Otherwise, the entire page would be covered in arrows, and we can't really afford to do it right now. But the point is that the electric field permeates the entire space, and wherever you put a charge, it's going to experience an electric force. If this charge had been negative, for example, then it would be the same scenario, but every single charge, every single arrow would be pointing inwards. Okay, but that's the main difference that you have to consider. So that is one way to think qualitatively of what the electric field is. It is basically something that permeates the entirety of space and acts on other forces. Now, that is actually something very interesting because this idea has been troubling scientists for a very long time, because this whole concept that the entirety of space is filled with something is very weird, right? How does something know? And so what physicists have been thinking about for many years, centuries even, is that, well, perhaps the entirety of space is filled with some sort of something, right? Some ether, they called it, that perhaps is rippled, right? When you have an electric field, perhaps there are ripples through it that are caused by this charge, and that is what another charge will feel as the electric field, right? They believed that this electric field required this medium that they call the ether. Much later, it ended up being other scientists, right? Michelson-Morley and most importantly Einstein ended up discarding entirely the concept of an ether. But for quite some time, this has troubled physicists. So if you are a little bit confused at first, don't worry. Now, why do we care about electric fields? Well, mathematically, they are a very important tool. We can use it to understand how different physical structures operate, but also because usually in a laboratory, you can regulate the electric field. It is quite simple to create an electric field in a laboratory. So it's important to understand, right, how do we change perhaps different setups to create different electric fields that will make our particles do something that we want, maybe in particle accelerators, or honestly in every single place where electric fields play a role, which is honestly everywhere. So all right, so that is just a little bit of a discussion about electric fields. Now let's go into the mathematical part. So how do we understand the electric field as a concept? Well, so let's put ourselves in a situation where we have a bunch of different forces. So let's put ourselves in a situation where we have just a bunch of different charges, right? So the total force that would act on a test charge Q, right? So force on a test charge, and I will name the test charge big Q because that's usually the letter that is used for it. But again, it's just a nomenclature. It doesn't matter if you use a different one. So the total force, right? The total force is going to be the sum of each individual force, right? Now, this isn't new. This is simply the superposition principle. Now, if I write this out, this is simply, well, force 1 plus force 2 plus, well, all the others. There may be 10, 100, 3, it doesn't matter. Now, what was the formula for an electric force? Well, we know that it is the constant 1 over 4 pi epsilon naught times the charge that is the charge that is generating this force, right? Q1 times the charge of our test charge, which is experiencing the force. Of course, everything is relative, but at least since we are looking at this charge Q like the one that we want to inspect, that's why I'm saying it in that way, divided by the modulus of the vector that goes from the position of this charge Q1 all the way to Q, right? So if this setup is something like Q1, and then we have Q2 and maybe Q3, and I'm not going to draw more because I'm lazy, and this here is Q, then R1 would be this, right? This is the vector R1, this is the vector R2, and this is the vector R3. So here we have to divide by the modulus of R1 squared, and we multiply it by the unit vector R1. And now we do the exact same thing, but for the second charge. So it's the same, but with a 2 instead of a 1. Okay, and of course, you go on and on and on with every single charge. Now notice that in every single case, we will have a factor of 1 over 4 pi epsilon 0 times Q. Okay, so we can factor that out. So we get 1 over 4 pi epsilon 0 times big Q, and then we have everything else. So then we have Q1 over the modulus of R1 squared times R1 hat, Q2 divided by R2 vector squared, the modulus of R2 vector squared, and then R2 hat, and so on. So what do we have here? What we have in here, right? What we basically get is we get this Q, which perhaps I will write on this side, just to make this very apparent. We have Q, the charge of the test charge, multiplying all of this. And this here is precisely what we will call the electric field, right? It is the contribution from every single charge that we have in the system. So rewriting this, we get that the total force is going to be Q times the electric field. And what is the electric field? Just to write it down very explicitly, the electric field is going to be the sum over all of this, which means 1 over 4 pi epsilon 0. And then we have Q. Now let's do this in a compact way. So we sum over I, so we get Qi, Ri unit vector, and Ri vector squared. Okay, so this is the electric field. Now it looks very nasty, but this is basically the electric field is the sum of all individual electric fields. So what is just one individual electric field? An individual electric field is simply going to be 1 over 4 pi epsilon 0 times the charge that is creating that electric field times the unit vector divided by the modulus of the vector that connects the source and the test charge squared. All right, so that is the case for individual charges. Usually what problems will be about is that you will have to find these three quantities. You will have to find Q, which sometimes is going to be easy, sometimes it may be a distribution of charge, as we'll see in a few minutes, and sometimes you need to find the unit vector r or the modulus of the vector r. And once you have all of that, you need to plug it back in, and never ever ever forget that the electric field is a field. It has a direction. Okay, so that's very important. So don't make the mistake of just plugging in some numbers, but not including the direction. Okay, that's very important. Now, what are the units of the electric field? Well, you can see it from here, right? The electric field is newtons per coulomb, which is one way to write it, or you can also use the SI, which is volts per meter. Now, in physics, actually, this looks like a W, so maybe let's rewrite it. In physics, we don't really deal with actual values for the electric field all that often, but if you ever need to come across this, these are two ways to use it. Which units to use depends on what exactly you are doing. If you are dealing with electric potentials, which we'll see later, you may want to use volts per meter. If you are perhaps using just charges and you are dealing coulomb, perhaps this is more easier. Anyways, that depends on what you're doing. Now that we have discussed point charges, let us move on to discuss distribution of charge. Because in real life, we don't really deal with point charges, right? We don't just deal with maybe just a small atom floating around, I guess in some situations, but usually we deal with distributions. So what do we do, for example, if we encounter some substance that is either positively charged or negatively charged? But the point is that we don't really know exactly. Perhaps we know something like the charge density, which we usually use a lambda in this case. This is the linear charge density, right? The linear charge density, which of course, this is simply the total charge divided by the length of this line of charge. I drew it in 2 dimensions, but of course, this is just to make it easier to understand, but it is one-dimensional. So it is divided by the length of this piece of substance. And how do we find the total charge? Well, what we usually do is that the total charge, this is simply going to be the integral of our charge density lambda, right? So this is going to be lambda, and then integrated over the entirety of our substance here, which we may just call, right? We may use the notation dl, which is very, very common. And for example, here, if this is 0 and this is L, you would integrate from 0 to L, or you could put the 0 in the middle, right? Maybe 0 is here and this is L over 2, and this is minus L over 2, so you integrate from minus L over 2 to L over 2. It doesn't matter. But the point is that you will often have to integrate, and these cases will be a little bit difficult. But all you have to do in the end is just plug in Q into our formula. I used large Q here, perhaps I should have used small q. But you would just plug it in here and then have to find, of course, the rest of the quantities. We will do enough examples in the future. Now, you can also have surface charge density, for example. Surface charge density, and that is the exact same idea, except that in this case, we are dealing with 2 dimensions and not just one. So usually we use the symbol sigma for surface, right? Lambda linear, sigma surface, right? And this is the same idea, the total charge that we have divided by the area this time. So the total charge is going to be the integral of, and now this is going to be a 2-dimensional, so maybe let's just say integral over the area, and we will have our sigma dA, right? So if this is a sphere, perhaps you have to integrate over the surface of the sphere, or if this is some sheet, you have to do integral in x and y direction, for example. It depends on what exact configuration you have. And of course, we can go to 3 dimensions to see just the volume charge density, which is going to be the same idea, right? Rho is going to be our charge divided by the volume, and thus the total charge is going to be the integral over our volume of our charge density, and then we integrate over the volume. You can use the v, some people use the tau. Again, it doesn't really matter. So that is the point. So what formulas do we end up with if we actually use this, right? So let's plug it back in here. So in the case where we have charge densities, for example, let's go for the linear. Instead of the point charges, we still have 1 over 4 pi epsilon 0. And then what comes next? Instead of q, right, we now have an integral. Now we have to integrate over whatever it is that we have, right? I'm just going to leave it as an indefinite integral. Of course, you're going to have to put the limits in later. All right, so maybe I'm just going to say that this is going to be over our L. So perhaps use L prime or something. Just use the notation that you want. And then we have lambda. And very importantly, the vector, right? The vector here, r hat, changes, right? So we will do an example of this in a few videos. But if we have this line of charge, for example, and our point charge or test charge is there, this is our test charge, Q test, just to make sure that we don't confuse it with that other Q, then what we have to do is that we have to take this little bit of line, for example, dl, and we calculate basically what the contribution is. And then we move on to the next little dl, right? And if this was the initial r hat, once we move a little bit, our r hat has now changed, right? And if we move to here, because we have to sum over this entire thing, then our r hat changes every single time, which is why we can't really pull it out of the integral. So our r hat will still be in there. So r hat dl, and for the same reason, as you can see, the length of this vector will also be changing, unless you just happen to be in a perfect circle or something. So we cannot really pull out the magnitude of the vector r either. So this is what the formula now looks like for the one-dimensional case. Now this may look scary, but don't worry. Everything that this is going to be about is going to be finding these vectors and plugging it in and solving just this one integral. Okay, it's going to be a lot easier than it looks. All you need to do is learn this formula and then apply it. Now for the other cases, it's going to be exactly the same, except that instead of having lambda, we are going to have either a sigma or rho, right? So the electric field is 1 over 4 pi epsilon 0. We integrate, and now we have sigma r hat dA over the magnitude of this vector r, and this is over A. And finally, then we have the electric field in a 3-dimensional case. So there we have integral over the volume rho r hat dV over r squared. Okay. Again, you may see notation a little bit different. Some people use this like r vector is equal to some weird r minus r prime notation. But it is perfectly equivalent, and I will show you how to deal with this in the next few videos where we do a few examples. So I hope that this video was useful to you, and if it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.